My research topic is on the Carboneras fault zone and taking a look at its internal structure and features that can be seen on the microscale. I will be going over a very brief introduction of the betic calderas which the Carboneras fault zone is a part of. Then I'll move on more specifically into the zone itself, where here I look at major characteristics of the zone and take a closer look at the microstructures occurring within the fault rocks in this area. So the Carboneras fault zone is located in the Betics region in southeast Spain, as you can see labelled CFZ at the bottom of the mainland in figure 1. The Betics makes up the northern branch of the Gibraltar Arc, and its structure came about due to tectonic activity in the Santonian/Campanian period, around 85 million years ago. There was oblique northwest-southeast convergence and collision between the African and Eurasian plate. This collision also resulted in the formation of the Alboran domain. The Betics region is subdivided into zones, the unmetamorphosed external and metamorphosed internal zone, which is highlighted in figure 2. The internal zone has experienced compressional deformation via thin skin thrusting. The Carboneras fault zone is a part of the internal zone, also known as the Betic zone, which is to the south. The zone is located on the Iberian Peninsula, southeast Spain, in the south of the internal zone of the Betics. The faulting in this zone is primarily consistent in the upper 5 kilometers of the crust, but the actual fault cuts all the way down into the mantle. There is just no faulting seen anywhere below the upper crust. Although, there are fractures present at depth, but they have closed up due to confining pressure and begin to reopen as it is exhumed to the surface. The first movement wasn't until the Miocene period, around 12 million years ago. The fault is a left lateral strike-slip fault that trends northeast-southwest. The fault is actually quite wide, being up to 1 kilometer in some areas. This fault, and a few other faults, such as the Palomares and Crevalente fault, make up the Trans-Alboran shear zone. As the Carboneras fault is strike-slip, we can then apply Anderson's classification. From this we know that the sigma 2 principal axis is vertical, but this classification only applies to coaxial deformation regimes and when the fault is mechanically isotropic. We know it's coaxial if the material lines remain in the principal strain axis. Only with these parameters can we then predict the fault pattern. The Carboneras fault zone is made of a wide variety of rock types, ranging from different layers with alpine crystalline protolith, dolomite basement blocks, 2 sets of Neogene age volcanics, low-grade metamorphic rock, and post-orogenic sediment. The fault cuts through all these layers and, as stated before, deep down into the mantle. The volcanics in this area consist of an older Neogene deposit around 25 million years ago and a younger deposit between 5 and 11 million years ago. The older deposit is tilted up against the fault and is near vertical, whereas the younger deposit is a horizontal layer. The fault zone is characterized by phyllosilicate-rich fault gouge and large dolomite blocks. Across the fault zone, there are 2 main strands of faulting, one in the north and south, and between these there are lesser faulting strands. These strands are anastomusing throughout the zone, as seen in figure 6. Here, we can see how all the bands of gouge are joint throughout and shows the different compositions of the gouge, such as mica schist, quartzite, and red sandstone. First, I think it's best to define what fault gouge actually is before looking in depth at its characteristics and microstructures. Fault gouge is a rock that is derived from tectonic movement. It is known as a tectonite. Tectonites are rocks that have been deformed in one way or another and exhibit features that tell us about their movement history. They are usually metamorphic. The movement that formed the fault gouge in the Carboneras fault zone was strike-slip movement. The boundary rocks were ground and crushed together in a process known as milling, forming the non-cohesive rock, the gouge. They are normally fine-grained and show less than 30% of themselves as fragments, tend to be part of the fault core. The fault gouge in the Carboneras fault zone is made up of the boundary rocks, which are mica schist, phyllite, marl, and red sandstone. The composition varies from place to place in the fault zone. In figure 7, the agua in medio exposure of the gouge is seen, and it is unique as it is well protected from rainwash due to this overhang. Overall, the fault gouge here is pervasively fractured and highly structured. The strands of the gouge are anastomusing throughout the zone, and figure 8 shows a model of the anastomusing gouge in the fault core. It also highlights the unique size of the fault core, up to meters in size, compared to other models which are on the centimeter scale. Around the core is the damage zone, which consists of large dolomite blocks. These are heavily fractured and deformed. The blocks are mostly bounded by the surrounding fault gouge, and they exhibit polished and striated surfaces, and it's common to see ultracataclastic rock within the dolomite. This formed from a process known as cataclasis. Pervasive mesoscale fracturing occurred that broke the blocks into decimeter-sized chunks. A study of these fractures suggests that they contain microstructural polycrystalline fragments within the ultracataclastic rock. In time, the surfaces were cemented and were then deformed by the fault. Within these two rock types, the gouge and the dolomite, they showcase different spreads of deformation in the fault zone. First, the gouge. It is split up into bands that show off a distribution of strain and deformation. This is a characteristic of strain hardening. Strain hardening is when a rock is being deformed, the strength of the rock increases as deformation continues. Due to this strength increase, the deformation looks for the path of least resistance and energy required. Hence, it is constantly changing path and spreading out the deformation within the rock. The strain hardening is also thought to be the reason behind the width of the fault. For the fault to widen, the strength of the fault rock must be greater than that of the country rock. Strain hardening most likely let this happen. On the other hand, the dolomite experiences zones of heavily localized deformation, which is a characteristic of strain weakening. These areas of weakening are important, as this is where seismogenic events nucleate. With the Carboneras fault zone showing these two types of distribution, it allows for the possibility of mixed mode seismicity, which is fault creep and fault slip. Now I want to have a closer look at the microscale on the fault gouge and dolomite blocks. The structures are in the context of simple shear. The fault core gouge shows off P foliations and R1 radial shears. These are kinematic indicators. The P foliation tends to form in grains that are obliquely aligned to the gouge zone. Lab experiments of fault gouge have found that these are the first features to form. The R1 radial shears also formed in the gouge at an oblique angle, but these are in the opposite direction to the P foliation. Both of these features in the gouge can be used to visualize the fault plane orientation and the associated slip vectors. This can be done using a stereoplot. As seen in figure 10, this is taken from two studies of the fault zone, and they both indicate a northeast-southwest trend showing left lateral strike. Another feature seen at the microscale are trails. These occur when particles are transected by local slip surfaces and traversed by cracks. This enables the particles to flow in a ductile manner. Similar to P foliation and radial shears, they are kinematic indicators and give a sense of shear. From experimental studies, it has been found that the last feature to form is Y shears. These are long shears that cut through the fault gouge with the same sense of shear. Slickolites are another feature to form in the gouge. These form from the process of pressure solution. The dolomite blocks also show R1 radial shears with respect to the orientation of the fault zone. Few R2 radial shears are present on the dolomite, but they are less prominent. These R2 shears form at a significantly larger angle from the fault gouge zone boundary, and they exhibit the opposite sense of shear. The orientation of R1 radial shears can vary depending on what rock the dolomite is faulted against. Dolomite vs dolomite, the R1 shears tend towards the fault zone boundary, whereas dolomite vs fault gouge tends to the Y shear direction. Overall, it ranges from 50 degrees from the fault gouge to being parallel with it. From these R1 and R2 radial shears, a max compression direction of north to south was found. Overall, the Carboneras fault zone is located in the internal metamorphosed zone of the Betics in southeast Spain. It is a 1 km wide left lateral strike-slip fault zone that is composed of a wide variety of rock types and layers. It is composed of anastomizing phyllosilicate-rich fault gouge, that is the fault core, and holds together large dolomite blocks. These two different rock types exhibit different distributions of deformation, dolomite having localized zones and the bands of gouge having well-distributed deformation. This is from its strain hardening property, which contributes to the fault's width. These rock types show microstructures that are kinematic indicators. These are P foliations, R1, R2 radial shears, and trails. The study of deformation mechanics and microstructures is important as we can establish parameters on variables that control deformation, such as temperature, stress, strain rate, and pore fluids, helping us understand the geological setting of faults. Today, recent studies show that the Carboneras fault zone is still active and moving around 1.3 mm per year. Here are my references.